Hello and welcome to the fourth video in this series. In this particular video, we're going to be looking at a completely new monoid on affine functions, which is a monoid under function composition and the identity function. In the previous two videos, we looked at the monoid under function addition and the constant function that returns 0. And we derived two analogous operations on the representation pair of rationals. If you haven't watched those videos, I'd suggest going back and looking at those right now. But today we're going to focus on deriving an analogous operation for function composition on the representation. So I've called it big circle to echo the small circle that is used to denote function composition. Just in case you're unfamiliar with the definition of function composition, it's this very well known definition here. F composed with g is a new function which at point x is f of g of x. Okay, so lambda x, f of g of x. Just like before, we're going to move in a forwards and reverse direction and meet in the middle, and hopefully we get things in such a state that we can recognize some similarity and just fill in the definition. So I'm going to work forwards first. And we're going to say, well, what is the meaning of f? How can we simplify this? Well, we know that f is f sub 1, f sub 2, big circle, g sub 1, g sub 2, applied to x. I can reload. I've made a syntactic error there. Reload. And that's gone through. And at this point, can't really go forward anymore unless I introduce a trick which I actually used in the last video, but not the previous video. And I've actually learnt something along the way, so I'm actually going to do it in this video. So you're seeing something that I've learnt in real time. So I'm going to say that let a comma b equal to this applied to this. I could even just say f composed with g, f large circle g, and then say in, and I'll indent everything by 2 spaces. And if I load that, that should work. So that will now allow me to write this. This is the meaning of a comma b applied to x. So that's nice. And I can go a step further, which is to say, well, what is the meaning of a comma b? Well, I know what that is. It's lambda x, a star x plus b, all applied to x. And actually, I'm just going to go one step further and just put a star x plus b. Well, that's nice. I'm just doing this because this will aid me in noticing some similarities that I need to fill in the definition. So now I'm going to start working backwards. We're working with known definitions here, so this is actually going to be fairly straightforward initially. We know that the meaning of f is lambda x, s star 1 star x plus f star plus f sub 2, function composed with lambda x, g sub 1 star x plus g sub 2, all applied to x. Now we can apply function composition. And we've seen what it is up here. It's f of g of x. So when I compose these two functions together, I'm going to get another one, which is lambda x. And it's going to be function f applied to g of x. Well, what's g of x? G of x is this, right? Then I'm going to apply f to that. Well, that's just applying this to that where x is. So it's going to look like this. And that whole thing is applied to x. That's gone through. So Agda thinks that's okay. And the way it checks that things are okay is it will normalize this expression and it will normalize this expression and then compare the result and see if it's actually the same thing. And it is in this case. So then I'm just going to simplify a little bit more and apply the x to this lambda expression, and then we'll just get this. So here we're actually applying this x up here to this lambda expression, which also happens to use the variable x. So this x gets replaced for the x in here. All right, lovely. It's just basic lambda calculus. So now what I want to do is rearrange this expression so that it's in the form a star x plus b. And then I'll know exactly what to fill in for this pair up here. So that's really nice. So I think the first thing I want to do is perform left distributivity over what's here, because I've got something times x and I've got this constant as well, and what I want to do is get it in a form where it's a constant times x plus b. So I'm going to need to do left distributivity, and I'm only doing it on a subset of I'm only doing it on a sub expression. So I'm going to need to use congruence. And I might actually explain what I'm doing with congruence a little bit more. I don't think I explained that 2 videos ago very well. So what I'm writing here is an expression where the white square denotes the thing I want to work on, and then the rest of the lambda expression is what I don't want to work on. It's the stuff I wish to leave alone. So here I'm saying, by writing this, I'm saying I do want to work on this part, that's the white square, and I don't wish to work on this part, which is here. So I'm going to put a question mark there, reload. I've got a syntactic error because I haven't written what I want to turn this into. So I'm expecting it, once I've multiplied it out, to look like this. And because I know about the associativity of plus, it will really just be that. So there we go. Sorry, that's F1 star G2. That's much nicer. Okay, so that's gone yellow because Agda's not quite smart enough to resolve all the constraints. But I know here I want to apply distributivity. And not only that, I actually want to apply it in the reverse direction. But let's just talk about, well, so it's going to be in the reverse direction, so I'm going to be using sim. So I can refine that. And then I want to apply this law here, which I already know about, which says that, sorry, I've got that wrong. It's star distributed over plus. I'm going to load and refine. Let's have a look at this, this theorem. So I'm going to press netta dot, and that takes us to this definition, which is inside data.rational.properties. And then the type signature doesn't actually tell me that much because it's using, I guess, what you'd call a type synonym in Haskell. So I'm going to meta dot further on that to get this definition here. And you can see that it says what you would expect it to say. It says for all x, y, and z, x star y plus z is equivalent to x star y plus x star z. So x left distributes over y plus z. So I'll go back to where we are. What I need to do now is fill in the x, y, and z. So that is going to be f1 G sub 1 star x and F sub, G sub 2. Reload and the yellow should go away. So that's really nice. Now, what do I want to do? Well, one thing I might want to do is reassociate the addition. So I might want to do this. So I might want to do this here. Just reassociate like that. So again, I'm going to have to use congruence. And this time, the part I want to touch... Actually, I don't have to use congruence here, do I? Because it's a top-level expression. So, yeah, okay. Actually, I'm just going to use plus a sock. In the reverse direction, I think I have to provide 3 question marks there. Nice. And this will be the first part of that associativity. The second part will be this. And the final part will be F sub 2. Great. So I've reassociated that. And the final thing I want to do is just reassociate this star here. So I'll copy and paste that expression up here. And I actually want that to be this, which is actually that, but I don't need to do that because of the precedence of the, sorry, I should say, yes, because of the precedence of the star operator. So this time I will need to use congruence, and the part I don't want to touch is here, and the bit I want to leave alone is here. And I'm now going to apply star a sock in the forward direction with F sub 1, G sub 1, and X. And now reload. Now I believe I have the proof in such a state that I can just read off the answer. So that is A is equal to F1 star G1, and B is equal to F star G2 plus F2. So I'm going to go up here, refine that, put F sub 1 star G sub 1 as the first element of the proof. Oh, sorry, of the definition. And F sub 1 star G sub 2 plus F sub 2 as the second element of the pair. Reload. And now we should be able to remove this bit here and see if the proof goes through. And so it has. And there is our definition for large circle. In the next video, we'll look at deriving an analogous operation on the identity function. So, see you in the next video.